Welcome back. Today we are taking a massive leap. We're transitioning from a simple consuming caching tools to architecting highly available distributed state. We're going to explore the macro architecture into atomic components and analyze the internal logic that allows system to serve billions. Don't forget to hit like, subscribe, and ring that bell icon to support the channel. And uh, head over to the companion website for us, which is bitbytoken.com. This is the website bitbytoken.com. The link will be in the description below. This has been further distributed into four different disciplines, which is core software engineering, data, machine learning, and AI engineering. Each of them will you can find fundamentals. If you want to identify fundamental, for example, for data, it is the Spark, which is again divided into basic, advanced, and expert. And then there is an implementation aspect, which is the example solution for these. We have tried to make it as comprehensive possible, but we welcome all kind of feedbacks so that we can make it even better. So let's jump on to our topics for the day, which is to identify the well, let's jump in. Okay, every distributed system has three walls, which is memory, throughput, and geography. RAM is finite, you can't fit terabytes into one motherboard. A single node peaks at about 200K operations per second. But modern platforms demands millions, and geography is the killer. A Tokyo user calling US East 1 faces an inescapable 170 millisecond round-trip penalty. To break these walls, we must redistribute. The big question is, who decides where the data goes? We have three main routing paradigms. First, Redis Cluster, where the server takes control. Nodes own part of the key space and routes client directly. Second, client-side sharding, where the application logic knows best, keeping the connection path as simple as possible. Third, the proxy-based router layer, where a dedicated intermediary like Envoy or Twemproxy handles all the routing intelligence. Each has its place in the architect's toolbox. Let's look at Redis cluster. It uses 16,384 hash slots. The formula is CRC16 mod 16,384, which ensures key deterministically land in the right slot. Why 16K? Because it creates a 2K bitmap that fits perfectly in the gossip protocol packets. And for multi-key operations, we use hashtags. Wrapping an entity ID in curly braces forces related key into the same slot. Client-side sharding uses consistent hashing. When you add or remove a node, you only affect the adjacent segment of the ring, preventing a global cache misstorm. It has zero network overhead because it is a direct client to node. But here is a warning zone. It's a coordination nightmare. If your different application instances run different sharding library versions, they will disagree on the ring state, and your cache will essentially vanish. Client-side sharding uses consist Client-side sharding uses consistent hashing. When you next look at the next one, the proxy layer decouples your application topology from your Redis topology. Legacy proxies like Twemproxies were simple, but they often broke multi-key operations. Modern proxies like Envoy are smarter. They can split multi-key requests into individual commands and route them to the correct shards. It's an extra hop, but it buys you immense operational flexibility. Now, how do you choose? Use this diagnostic matrix. Redis cluster is best for general purpose single region setups. Client-side sharding gives you ultra-low latency for pure caching. Envoy proxy is the power user choice for serverless mesh environments where you need circuit breaking and complex routing. Never forget the speed of light limit. Redis processes request in under a millisecond, but the network is the entire bottleneck. If your cache is in the US East and your user is in Tokyo, a 160 millisecond round trip is a catastrophic violation of your SLA. The only real solution is geographic proximity. You must put the data next to the user. For geo-distribution pattern, one is active-passive replication. One master region handle all writes and remote region get asynchronous read-only replicas. It's simple, but it carries a latency tax. An e-commerce checkout happening in a remote region suffers a 100 millisecond plus penalty writing back to the master. It's perfect for read-heavy workloads, but breaks under write-heavy global demands. Pattern 2 is the active-active mesh. Every region except both read and write locally, zero latency tags. The danger? Concurrent write collisions. Without conflict resolution, different regions will converge to different values, resulting in a silent data corruption. This is the classic CRAP theorem trap. The fix for active-active is conflict-free replicated data types, or CRDTs. They are mathematically designed to converge to the exact same final state, regardless of the order in which the update arrives. Whether you are using G counters for tallies, last write wins for strings, or union semantics for sets, CRDTs ensure your distributed state stays synchronized without coordination. To survive in production, you must defeat the thundering herd. If thousands of keys share the exact same TTL expiration, their simultaneous expiry crashes the database. The fix is TTL jitter. Always add a randomized time variance, say 15% to your expiration time. This spreads the database reload load across a wider window and ensure your system survives. If you're ever stuck, use this diagnostic matrix to find geo strategy. Start with the read-write requirement, consider your infrastructure constraint like Kubernetes or legacy code, and move towards the right solution, whether that's active-passive or proxy layer or a specialized active-active CRDT solution. Before you deploy, run through the senior engineer checklist. Characterize your read-to-write ratio. Design your key schema with hashtags. Be explicit about your consistency versus latency trade-offs. And crucially, plan for partitions. What happens when the cross-ocean links servers? Master these patterns and you'll transition from consuming tools to designing systems that serve billions. Any questions on these strategies? Let me know in the comments. And don't forget to like, share, and subscribe. Until next time, thanks for watching. Bye.